Hey everybody, this is Mrs. Rajewski. Today we are going to be talking about the integral test and the p-series. So let's go ahead and get started. The integral test is a way for us to look at the integral of the series and see if that's convergent. And if it is convergent, then the series itself is convergent. And if it's divergent, then the series itself is divergent. So we've actually already looked at integrals by themselves and calculated those to infinity and to find the area under the curve. And now we can do so with sums as well. So let's get started. Basically, everything I just said means if the area under the curve as x approaches infinity converges, then the series is converging too, and it works the same way for divergence. So we can take something like this problem where we're looking at the sum from 2 to infinity of 1 divided by x times ln x. And we can actually start by letting a sub n be equal to 1 divided by x ln x. And then we can take the integral and see if this integral is going to converge or diverge. Now, the whole premise of the integral test is based off of whether or not, or starting with a function that's continuous, positive, and decreasing from 1 to infinity, or whatever your limits of integration are. So we want to look at this and make sure it is 1 divided by x ln x, a positive decreasing function that's continuous. So let's go ahead and test it out and see if this looks like a continuous positive and decreasing function. So one way we can do that is through using our calculator. So I'm going to pull up my calculator and I'm going to see what exactly is happening here with the graph of 1 divided by x ln x. Let's check it out. Remember, I'm looking at this from 2 to infinity, so I'm really, obviously what we have here is an asymptote at 1, which is why we're not starting at 1. We are going to go ahead and start at 2. And this is a positive decreasing continuous function. So I can actually check this off. We have a positive continuous decreasing function. And now we can calculate the definite integral. So let's go ahead and get started with that. We've got the integral from 2 to infinity of 1 divided by x ln x dx. Well, this is an improper integral, so I'm going to transform it so that I'm taking the limit as b goes to infinity. And you can use any variable here from 2 to b of 1 divided by, I'm going to split this apart here. So I've got 1 divided by x times 1 divided by ln x. Do you see how this is the same thing? I hope so. Don't forget your dx. That differential is important. So when I look at it like this, and I'm about to take the integral, I see that this is like a product. And one strategy that we use to calculate integrals of products is we use U-substitution. So I'm going to try a U-substitution here. And I'm going to let u be, let's let u be ln x. Because when I take the derivative, well, the derivative of ln x is 1 divided by x. Do you see how those pairs are here in this problem? So here I've got 1 over x, which is part of our du, and also dx, the other little bit. And then I've got my u value right here. So let's go ahead and rewrite this using our u substitution. So I've got the limit as b goes to, oh, my infinity symbol got kind of weird looking there. B goes to infinity of the integral from 2 to b of 1 over u du. Again, 1 over x dx is equal to du. So I can take that piece out and substitute in a du for it. And then ln x was my u value, so I'm just substituting in a u for my ln x. Now the reason I did that is not because I'm crazy and I prefer to work with u's, but because it's much easier to take the antiderivative of 1 over u than all this other stuff. So let's actually go ahead and do that. So I've still got my limit in the front. And when I take the antiderivative of 1 over u, I'm going to get ln u. And remember, when you take the antiderivative, what's in your argument has to be positive, so we're going to put our absolute value symbol in there. And we're going to calculate this from 2 to b. And I prefer replacing my u back in instead of replacing my upper and lower limits of integration. So let's go ahead and continue by replacing our u value with our u, which was ln x. So let's see, this is going to be ln, not of u, but of ln x. And I'm going to use parentheses now because I know that with my limits here that I'm only going to be looking at positive values for x. So, okay, so now I'm going to substitute b and substitute 2 and subtract these guys. So I've got now the limit as b approaches infinity of ln b, goodness me, minus ln 2. Okay, so let's take the limit now. Now, as b goes to infinity, this is going to keep growing and growing and growing. It's going to get bigger and bigger. And I actually tested it before I did this video, and I tested it with 10 and it was a little number. And I tested it with 100, I got 1.5. I tested with 1,000, I got 1.93. And I realized that after testing 10,000, I was only getting 2.22, that it is growing slowly. But it's growing nonetheless, and it's never going to stop. So this does not exist for a limit. It's just going to keep getting larger and larger and larger. Whereas this guy is just a finite value. It's just a constant. And I don't really care what it equals. I know it's a constant. But as long as this first one is growing and growing and growing, the limit does not exist. Okay, so we don't have a limit. What does that tell us? Well, if we go back to the integral test, if the integral from 1 to infinity, or in this case 2 to infinity, is divergent, which is what this means when the integral does not exist, then the sum of the series does not exist as well. So hence the series diverges. And that's the integral test because, you got to take the integral. If you get an answer, then you've got a convergence. If you don't, then you got a divergence. This is just one other way for you to test to see if an infinite series will converge or diverge. All right, let's try it. So let's use the integral test to determine this one. Wow. So on the last problem, I was just using graphing to solve, which is nice because, if you've got your calculator, it's an easy way to do it. But what if you actually have to prove that the series is continuous, positive, and decreasing? Well, just right away that this is going to be a positive series because n is going from 1 to infinity. So this is going to be positive. And e to whatever power is going to be positive as well. So we definitely have positive. And we also have continuous. There's nothing that's going to cause an asymptote n is just a constant value, and e to the negative n squared power, well, this that exponential function, and where our asymptote is going to be is not on this interval. So we're good there for continuous. So really what we need to show is that this is a decreasing function. The best way to show that it's a decreasing function is to take the derivative and see what's happening there. So that's what I'm going to do. I'm going to let f of x equal x e to the negative x squared power. And so the derivative, well, I'm going to have to use the product rule, right? 1d2 plus 2d1, the product rule. It's so much fun. So let's go with that. 1d2, so the derivative of e to the negative x squared is e to the negative x squared. But then we have to apply the chain rule so that we take the derivative of what's inside. So the derivative of negative x squared is negative 2x. So that's 1d2 plus 2, that's our second factor, d1, and then the derivative of x is 1. And I'm looking at that, and I see that in both of these terms, they've got this e to the negative x squared. So I'm just going to factor that out. And what's left over is x times negative 2x, which is a negative 2x squared. And when I factor it out here, I'm left with this 1. And it's positive because I got a plus sign here. Okay, well, there's the derivative, but in order for me to figure out if it's increasing or decreasing, I need to find the critical points. That's going to be where it crosses the x-axis. So I'm going to use the zero product property to find where it crosses, where the derivative crosses the x-axis. So I'm going to find those critical points. And they cross the x-axis where it equals 0. So I'm going to set e to the negative x squared equals 0. And negative 2x squared plus 1 equals 0. Now again, e to the negative x squared, this is always going to be a positive result. It could get really, really ridiculously close to 0, but it's never going to actually equal 0. So that doesn't exist. No. But over here, I can subtract 1 on both sides. So I've got negative 2x squared equals negative 1. I can divide both sides by negative 2. And this is going to give me x squared is equal to 1/2. I could take the square root of both sides. And this is going to give me x is equal to plus or minus 1 square root of 2. Now, I know that my x value, or in this case the n value, is going to go from 1 to infinity. So I'm really not that interested in what's happening with a negative 1 divided by the square root of 2. But I am interested in the positive side because anything that happens here is going to continue happening after 1, and after 2, and after 3. So if this is my critical value, then I want to know what's happening to the right of that. So you can substitute in a 1 or substitute a 2 into your derivative function and see what happens. Now, I don't care what the value is. I just want to know what the sign of it is, because if it's positive result, then I know I have an increasing function and I can't use the integral test. But if I substitute one of these values in that's to the right of our critical point and I get a negative result, then that will tell me that we have a decreasing function. So I just subbed in 2 and I'm just thinking about it. I'm not actually substituting it in. If I've got e to the negative 2 squared power, so 2 squared is 4, e to the negative 4th, this is going to be a pretty small number, but it will be positive. Then over here, if I substitute in a 2, 2 squared is 4, 4 times negative 2 is negative 8, and negative 8 plus 1 is negative 7. Negative 7 times a positive number is going to be negative. So what this tells me is that to the right of my critical value, I've got decreasing functions. So I'm decreasing. All that work just to show that yes, in fact, we can use the integral test. But if you're taking a test and you're not allowed to have a calculator, this would be how you would do it. Okay, so now let's move on to step 2. Now we're actually going to be able to apply the integral test. So here we go. We're going to take the integral from 1 to infinity of n e to the negative n squared power dn. And this looks like it's going to lead me towards another U-substitution. Since it's an improper integral, I'm going to take the limit as b goes to infinity of our integral from 1 to b of n e to the negative n squared power dn. Yeah, I'm going to go ahead and use the a U-substitution again. I see a product. I like using a U-substitution for products. I like integration by parts when I'm seeing chain rule action. So let's try a U-sub though. So in this case, I'm going to let u equal my negative n squared. That means that du is going to be negative 2n dn. And let's get that dn alone. Let's see what's happening here. So that's going to give me, let's see, du divided by negative 2n. And that'll give us dn. All right, so let's use this U-substitution here. I'll move this up so we can see the whole thing. So, all right, I've got the limit as b goes to infinity of 1 to b of, let's see, I've got n times e to the u power, and then dn is really du divided by negative 2n, so times du divided by negative 2n. And you can see here that these n's divide and make 1, so they're out of there. So let's rewrite what we do have now because it looks a little sloppy. I have the limit as b goes to infinity of the integral from 1 to b of, let's see, this is a dividing by negative 2. That's the same as multiplying by a negative 1/2 e to the u du. That looks nicer. Now this I can take the integral of rather easily. So can you. So let's try it. We've got the limit as b goes to infinity of, now we're taking the antiderivative, so I've got negative 1/2. All right, I love taking antiderivatives or derivatives of exponential functions at the natural base because they just say their own name. That's e to the u. And we're taking that from 1 to b. Now, I like to substitute in my u back in instead of changing my upper and lower limits of integration. So that's what I'm going to do. I've got the limit as b approaches infinity of negative 1/2 e to the power of, remember e to the power of u was negative n squared. Fun times. All right, let's go ahead and substitute in our b and our 1 into this problem. So we've got negative 1/2 e to the negative b squared minus negative 1/2 e to the negative 1 squared. Well now, I think that this actually looks a lot nicer when we get rid of these negative exponents and put them down into the denominators instead. You don't have to do that, but oh my goodness, my arrows are terrible. Using the tablet does not improve my drawing skills. One would have hoped, but no. All right, so I'm going to put these into the denominator. So I've got, let's see, -1 divided by 2e to the b squared power. I just think it's a little bit easier when you're about to take the limit. 2 negatives make a positive. And then I've got 1/2 e to the -1 squared. Well, okay, 1 squared is 1. So e to the -1 power is just going to move that e down to your denominator. You know what time it is? It's time to take this limit. So let's go ahead and do that now. Now this is a constant. It's going to stay a constant, so we don't need to worry about that. But how about here? As b goes to infinity, so as b gets bigger and bigger and bigger and bigger, e to that really, really big power is going to get even larger. And then we're going to multiply it by 2. Can I hear getting bigger too? All right. Then, but that's all a denominator. So -1 divided by a super gigantically growing number is going to have a limit of 0. So I've got 0 plus a constant. This is going to converge. And what that tells me is that the series converges as well. And that, my friends, is the limit comparison test. Woohoo! All right, so let's move on to using the limit comparison test to help us with a P series. This is example number 7. So previously, we looked at a series like this, and we were proving the convergence of an integral. But now we're going to prove the convergence of the series itself. So we actually investigated this on page 20 in our notes. And we came up with a lot of ways that we could look at this problem. And we said that, well, here, I'll put it in. So if, instead of writing it all out by hand, this is much faster. If P was less than 0, we actually had already investigated this all. Then the limit didn't exist, which meant that it diverged. If P was equal to 0, then the limit equaled 1, which diverges by the nth term test. And then if P was greater than 0, 3 situations occurred. Now, we investigated all 3 of those situations back in on page 20 in our notes, and I'll link to the video too, so you guys can see that as well. But if P is greater than 0, 3 things happen. We get either 0 is, or P is in between 0 and 1. Okay. And in this case, it diverged. Again, the proof will be on page 20 in your notes. We also could have P is equal to 1. And in that case, it also diverged as well. And then we had a situation where P is greater than 1. And when P is greater than 1, we were actually able to show that it converges. So we said, therefore, the sum from 1 to infinity of 1 divided by n to the p is convergent. For all p greater than 1 by the integral test. And we can stop there, but of course I'm not going to because I have the opportunity to show you the integral test in action. So let's go ahead and do it. Let's show for this particular case where p is greater than 1 that it converges. All right, so here we go. We start by, obviously it's called the integral test for a reason. We're going to take the integral. So let's integral up. We've got the integral from 1 to infinity of 1 divided by x to the p power dx. And then we've got the limit as b goes to infinity of the integral from 1 to b of 1 divided by x to the p dx. So I'm working with x instead of n, that's fine. Again, we're taking the limit because this was an improper integral. All right, now we get to anti-differentiate. That's cool. This is just a power rule. So I'm going to take the limit as b goes to infinity of, let's see, this is really x to the negative p power. So if I want to take the antiderivative, I'm going to add 1 to my exponent and then divide by my new exponent. And we're going to take this from 1 to b. Okay, so before I take the limit, I see that this whole denominator doesn't even have any x's in it. So this is really not going to affect my substitution of 1 and b in there. So I'm going to just pull that out to the front. This is one of our rules of limits that we can use. And then we can just multiply it to our result at the end. So the limit as b goes to infinity of, much easier to calculate, b to the, oh, I can actually go ahead and substitute in my b and my 1 now. So b to the negative p plus 1 power minus 1 to the negative p plus 1 power. Cool. So it looks like we are ready to take the limit. If remember, we're looking at p is greater than 1. While we're taking the limit. So we have 1 divided by negative p plus 1. Well, this is just going to be whatever 1 divided by negative p plus 1 is. As long as p is greater than 1, this is just going to give us a negative constant. It's not really going to change, and it's going to multiply by what's inside. Now, b to the negative p plus 1, this is interesting because it's kind of like 1 divided by b to some constant value, right? Because if p is greater than 1, like let's say it's 2, then negative 2 plus 1 is a negative 1. So it's just going to be something that's in the denominator, but when we move it to the denominator, that result up here is just some constant number. This limit is going to go to 0. And then we've got good old negative 1 to the negative p plus 1 power. Well, I'm going to subtract 1 to the negative p plus 1 power. Well, I don't care what value you plug in for p here. Let's say it's 10, all right? So I've got negative 10 plus 1, that's negative 9. 1 to the negative 9th power is 1. And so it's always going to give you this limit of 1. And since it's being subtracted, that's a minus 1. So what we really have here when we take the limit is going to be whatever 1 divided by negative p plus 1 is times -1. That converges. That's going to be a result. If I know what P is, right, then as long as it's greater than 1, we have a converging result. It's a done deal. That's your integral test in action. All right, now one final note, this particular series is a special series. It's called a P series. They're very useful, and now that you have investigated them thoroughly, you can now call that the P series test. So you don't have to show that all that work I just did. You never have to do it again. When you see a P series, again, something that's in the form where you've got your x or your n to the p power, so some kind of power, then you can just call this the P series test. And it converges if the exponent, or your p value, is greater than 1, and it diverges if your p value or your exponent is less than or equal to 1. And there you go. So new tests that came from the integral test. Now there's a special form, the situation when p is actually equal to 1. It's a harmonic series, and it's got lots and lots of useful functions, but most importantly, it's actually the reason why we can't assume a series is convergent just because the limit as x approaches infinity is 0. Because the limit as x approaches infinity of 1 over x does equal 0, but we in fact know that it's a divergent series from our prior work. So don't forget that. It will probably pop up. And if I know me, I would probably put it on a test. So there we go. Those are our next two series, and or convergence tests rather. And we will go on and talk about alternating series in our next video. Please make sure that you do your homework. My preference is to do the Mind Lab and Mastering, but if you don't have access to that, go ahead and do our problems out of the textbook. Thanks, and I'll talk to you guys later. Bye-bye.